And so we'll talk about local or online planning, and this is part one of it. Just a gentle introduction to it, why we are doing, what's the big deal, and what are some basic ideas underlying it, and then we'll see. So the motivation is very simple. Life is too short, the world is too big, you can't see all the states, let alone seeing all the states multiple times. Or, to be a little bit more precise, so we want to have an algorithm that we can use to control some system. And the high level problem is just that we should have access to some description of the system, some way of accessing, getting information about the system. And then we want to control it. What does it mean that we want to control it? It just means that, well, we want to maybe output in time an action that overall leads to good policy. And in the previous lectures, we're looking at the kids. What was this sound? Me? I don't know. We are looking at algorithms, value iteration, policy iteration, that make it look as if like we could read big tables, or like these tables that describe a Markov decision process, and then process them, and then compute a policy at every state. Well, of course, this is going to require touching every state at least once. What if you have too many states? No, we have to realize that we never wanted this. So first of all, we didn't really need to pre-compute how to act at all the states. If we demanded that we should do this, then of course, just writing down what you need to do would require time that's proportional to the number of states. So if this was really the goal, this goal cannot be done unless unless S is small, or maybe you have a compact representation for policies, but you can't really have that in general, so without further restrictions. And so really the realization is that maybe you don't need to do this. Maybe the real thing is that a state arrives and then you just want to do some computation, output an action, and then go on with your life. So you want just an action at a state, which is part of the input. So you're localizing to that state the computation. So this is why I call this local planning. So my computer keeps beeping. I don't know why is that. Sorry about that. Do you hear it? I put it on do not disturb mode, but I guess these days it doesn't matter what you tell your computer, it's doing its thing. Anyways, it has its own life. It's an intelligent agent, perhaps. Anyways, so local planning, online planning. And okay, so the other part of this is that if the MDP was really represented by these big tables, then you need to read the tables to know where the information is. It happens that if you have simulator access to the MDP, then this problem goes away, which is really interesting. So we're changing the representation of the problem. Complexity changes. All right, so this is just a picture that I took from some other talk that explains what I already talked about, that there is the word. This is this big MDP here. So this is the word. And there is the current state that's coming from it. And given the current state, you just have a planning algorithm that can be called. with the state and maybe a required precision of like how optimal your policy should be. That's your target. And this planning algorithm will have access to a simulator, which will show me the faithful representation of the MDP. And it can send queries to this simulator of the form of state action pairs, to which it receives responses in the form of next states sampled from the transition probability and the reward associated to that. So this is how piece by piece this planning algorithm that is implemented under this function get action can gain information about the MDP, and eventually maybe you should stop querying the simulator and then it needs to produce an action. Once that action is produced, it can be sent back to the environment, the loop is closed, and in this way, your planner kind of implements a policy. By the way, previously you were asking me about like what's the deal about this memoryless policies and whether we need history-based policies or anything complicated like that. Well, a lot of these planning algorithms could have some internal memory, so they can save data between calls. And if they would do so, then they would have memory, and then the policy that they implement, it would be a history-dependent policy, right? It can also depend, it also depends on a lot of other randomness. So the planning algorithm itself could flip coins, but it's calling this MDP simulator that responds in random way. So a lot of further random way, if you want to talk about, what happens here, then you need to introduce a bunch of other random variables. And then there were these questions about this probability space being large enough or not large enough, the one that holds at least the trajectories, and in which you can assign this joint distribution over the trajectories. That depends on the policy that you chose and the MDP. So now this is a situation where the canonical probability space wouldn't really cut it if you want to talk about this added randomness. So in responding to the Slack question, I was just saying, well, an algorithm could just like flip some coins, and then if you want to represent the results of those coin flips together with the trajectories, then you need a space that is bigger than the canonical space that would just hold the trajectories. Anyway, so this is an example where that space would be bigger. But by the way, like we are generally, it's like even though this space is there, because that's how probability theory is done, we never really talk about these spaces, and we just assume that they are there. They can be constructed in some way. All these probability distributions can also be constructed in some way, and people just don't even talk about them, right? So if you read a paper that is written about reinforcement learning, even if it's written by a person who cares about mathematical precision, they wouldn't mention any probability spaces. And probability theory papers are written by saying that, oh, let x1, x2, xn be IID random variables. There is no mention of probability spaces. It's all under the hood. And the reason you can do this is because of these theorems of Kolmogorov's theorem and this Tuchaska theorem that assures us that as long as you're just like imposing conditions on random variables and you're not introducing any inconsistencies in these conditions, there's always a probability space that can hold these random variables, and there is always a joint distribution that you can put on this probability space that satisfies all these requirements. So this is why we don't really talk about these probability spaces, and we don't mention them, right? Because it's just like once you learn these theorems, like there is no need to mention them. in a way. All right. And so this is what we're going to do a lot. So we will stop mentioning probability spaces, except for a few cases where we really have to go back and then think hard about these probability spaces. There are some occasions like that, but most of the time, for most purposes, we don't need to worry about that. Okay. You might still ask, then what is the fuss? Well, you want the symbols that you're writing to have some meaning assigned to them, which is well defined, right? And it is only probability theory and this build-up using Kolmogorov's system that assigns a consistent meaning to all these symbols that people are writing. There's no other system. This is the only system that we have. And it's just like swept under the rug for most of the time, because for simple cases, it is trivial to do things in some other ways. But if you, like have infinite coin tosses, for example, then there is no way around it. All right. Okay. Okay, so this is online planning. The task is to write the function getAction. Okay. And the objective of writing this getAction function is such that for the policy pi, which is induced by using this getAction function in this closed loop fashion, so that induces a policy, right? It's maybe not a memoryless policy, but it's still a policy. The value of this policy is at most delta away, no matter how you start it, from the optimal value. So that's the objective. And so a planner is really just like, what is the algorithm in getAction that makes this happen? Okay. Any questions for this?
So I guess I have a question here. So in the definition, we are not mentioning that there is this requirement that the output state should be part of the whole probability space for states, and but we are mentioning that like state by action should be part of the like MDP simulator state action space pair. So my question is that when the simulator outputs one state, it could be an unreal state, right? It's not like the simulator could be a noisy simulator and it could have some error, and then the output state for the MDP simulator could be an unreal state, right? So in that case, how can we make sure that this objective will hold and we will get to a policy that the V pi is no delta?
I guess you're talking about that the MDP simulator
Yep.
may not be perfectly simulating how the world
Yeah.
works.
Yeah. And the output state could be some like
Right.
unreal state that we cannot fix the value of it.
I mean, it's not about whether the output state is real or unreal. I don't know how to interpret that. But it could be that its distribution, given the state and the action that was the input to the simulator, is not the correct distribution, right? So maybe you're talking about that. Okay, the distribution couldn't go to this place, and then in the real world, but in the simulator it happens. Anyways, the answer to the question is that garbage in, garbage out, right? Like in general, if you have a simulator that has nothing to do with the world where you need to act, there is no algorithm that is going to do anything about that. There's no way to fix if everything is broken. If not everything is broken, then the question is, okay, in what way not everything is broken? And so there you can say things that, okay, let's assume that you have this simulator, and that is the real world. So in the simulator, you have P tilde and R tilde. So this is what it simulates. The real world is P and R. And so now we can say that, okay, if P tilde would be close to P, oh, sorry. So if P tilde would be close to P, in some sense, and R tilde would be close to R. So let's say the maximum of these two differences in some norm are small. Does this mean that if I write an algorithm that uses this simulator as if it was the real world, like it's not really compensating for any of the errors, so we use it and derive an algorithm pi tilde, or like a policy pi tilde. And if we use this pi tilde in the original MDP, so it's like, okay, this is also a policy in the original MDP. And so that in that MDP, this is M, and this is M tilde. And so maybe what happens is that this is a good policy in M tilde. So in M tilde, it satisfies this requirement, right? Then the question is whether it's going to satisfy some good requirement, like it's going to have some good properties in the original MDP. So then you can just write that, okay, this is nothing but this, and if you have a simple enough policy, then a lot of times what you can do is that you can relate for any policy if there are two MDPs. So you want to translate this to M tilde. So you can write as that the value of policy pi tilde in MDPM is, well, we wish it was the value of policy pi tilde in M tilde, but it's not. So we have to compensate for this. So we have to subtract this. Okay. And we know that this is good. This is a big value in M tilde. So in M tilde, this is near optimal. Okay. So we can lower bound this, the first quantity, by this value. And now you could say that, well, okay, but how does this relate to the value in M? So there you can play the same game. You can say wishful thinking, this was M, and then there is a difference that results from lying here and using M instead of M tilde. So we had M tilde, so we have to put that back. And then there is this difference. And so now we have to bound this difference, this, and this. And these are continuity questions. The question is, okay, if I have a policy, I fix it, and I just change my MDP. But I can't change it too much. So let's say that this difference is at most epsilon. How much will the values of the two policies change? And it happens that you can bound this as a function of epsilon. So there is continuity. It's because of the contractions that we have, and it's not too hard to do this. So you will find that this in supremum norm, this difference, is upper bounded by, I don't know, epsilon over 1 minus gamma. And similarly, you can find that this is upper bounded in supremum norm by epsilon over 1 minus gamma. So now you can add everything together, and you will see that your policy in MDPM, even though it was calculated for or optimized for M tilde, is almost as good as the policy here, except for this data and 2 times this epsilon over m, 1 minus gamma, if you add everything up. So as long as your epsilon is controlled, as long as your delta is controlled, everything is under control. So this is why we don't, in general, worry too much about this discrepancy. But maybe one could do more. Maybe one could. So, for example, this domain randomization ideas that people are trying, right? So this is what's called the sim to real gap, or whatnot, like modern terminology. But like this is ancient. But okay, so people, for example, have proposed to deal with this gap by demanding that the policy that somehow we read out by interacting with the simulator should be good not only for this simulator, but it should be good for many different versions of this simulator, right? So it's kind of like having a worst case guarantee over a different parameter. So for example, if I introduce some parameters here, theta parameters, there could be like friction and like various physical quantities which are not known precisely. But if we knew them, then like the true MDP also has some parameter, and it is just not known which of these parameters gives the true MDP. So now we have this parameter set, theta, and so you can play around with that. So you could demand that even for the, like you want a single policy that is independent of these parameters. You want a policy such that no matter this parameter, this policy in all of these MDPs is near optimal for all of the theta. So you can have a reinforced goal, and you can try to work out an algorithm to achieve this reinforced goal. Because if it has this, if you're able to come up with something like this, then the true MDP is just one of these guys. It's theta star. So it's going to have this guarantee as well. But maybe it's not so simple to come up with a single policy that achieves all of these goals. Maybe it's impossible, right? So you have to realize that, well, this can be conflicting. This can be also conflict, like these different MDPs. They're like possibly unrelated. In one MDP, going left is optimal. In the other MDP, going right is optimal. So you can't have all of this. And no, you have to figure out something. So what people were proposing is that maybe you take an average over the theta, so that's the domain randomization. I'm not sure that that's really a good idea. Maybe you close the loop. Maybe you're gonna, I don't know, tune the theta and like get a policy, tune the theta more. So there are multiple ways of going deeper than just to say that, okay, I don't worry about this. In general, I think it's still very valuable, like just not to worry about this and just to do as if the true MDP and the simulator were really the same, because there's a lot to be learned about how to design these algorithms, even for that simple setting. Plus, we have this basic guarantee as well. And then maybe on the top, we can later on build things. Okay. Good. So that was a good question. Glad you asked it. You're happy with the answer? Okay, good.
Yeah, definitely. It was very helpful. Thank you.
Okay, good. All right. So a little bit more about these. The slide is not updating. Okay, it updated. So a little bit more about this get action function. So later on, okay, so this is not really that relevant at the moment, but But later on, when we talk about interacting with really, really large state spaces, we're going to bring in features and linear function approximation. And then there will be the question of like, how do you access these features? And here we have like various ways of simplifying our life. So for example, you could have this very simple thing where you can just query all the features at all the states, but that would require enumerating all the states, which is silly because this is what we wanted to avoid. So it's, yeah, we do this for the sake of just, as thinking experiment. We know it's not really real. You can't generally do this. And the other thing is where can you query the simulator? So can you query the simulator at any state, or you can only query the simulator at particular states? Like, how do you even know what states exist in the world, right? So there is surely this state that came in, but how about the others? Well, up to now, we used the convention that, well, we said that we're going to talk about mostly finite MDPs. And then without the loss of charity, we can just assume that the states are numbered from 1 to a natural number. But how do you know how many states there exist at all in the MDP? So what if you say, if you tell the simulator, give me state 100 billion 22, and the simulator just says, I don't know, what is that? Like, what are you talking about that? Also, you would need to write a simulator with an interface that can translate from these integers to its internal representation for the states, and back and forth. So it's like some non-trivial interfacing issues exist. So, for example, just to ground all of this. So imagine you want to write a simulator for a robot, right? And the robot, what are the states? The robot is maybe, picking and placing objects in a 3D space, and there are various objects which could be described geometrically in the simulator. And the robot has this enclosure, and it's like it's a robot arm. It's just a robot arm. It has a fixed base, and maybe it has a gripper. So it has these joints, and then they have angles, and then it has this gripper, and it can grip stuff. And it's in this enclosure, and it has a cage, let's say. So it can't get out. Like, it tries to get out, and then it bumps into things and like can't get out, right? So the states would be like, what are the states here? So first, there is the configuration of the robot. Like, what are the angles of the various components of the arms? So that's definitely part of the state. Also, this is classical Newtonian mechanics. So there is a second order dynamics according to Newton's laws. So you not only need positions or angular positions for the robot arm, but you also need velocities to describe the state. So you're going to have, okay, theta has a different meaning here. It has angles, and it also has angular velocities. And it would also have, like all these objects that it can manipulate. Maybe this is like a bag, and then it has this ear, and it can be grabbed by it. And like, we also have a big pencil here. It's a huge pencil, and so on and so forth. All kind of stuff, like maybe a shoe. Complicated things. And whether some object like that is there or not, and everything that describes its physical characteristics, it's like, what's its orientation, and like how it's configured, like what are these little parts. everything goes into the state, including maybe the velocities, because maybe the robot is going to throw it and it's going to fly and it will have some velocity. And when it's lifting, it has some velocity as well. And so everything goes into the state. And some states are not physical because the robot is in this enclosure. And if it has all these solid objects around, then if it bumps into them, it cannot penetrate into them. So some configurations of the angles are going to be forbidden. So now imagine trying to translate this mass into just integers. Like the states are numbered by integers. Or even if you, I don't know, like what representation do you want to use? It's going to be crazy, right? But here the interface is really simple. Like we want states to come in, we want our algorithm to be able to process what state means, and so on and so forth. So this is a mess, right? Like this global access is really, really hard to achieve. So here we should be able to query the simulator for like, okay, what are the states in U? And then we should be able to point to any of the possible states and then tell the simulator, go there and simulate for this action what happens. But that's really hard to do, just because just describing the state space itself is hard. Okay. But we can still write the simulator. There's no problem with writing the simulator for this setting. It will just be hard to describe completely the state space, let alone, like the finiteness is really biting us here. But I mean, the finiteness was important at the beginning because it allows me to simplify certain parts of the math that we're doing. But we already talked about it, is that it's generally not that important. But when it comes to, like implementing stuff like this, it's like you have to agree on an interface of how you're describing the states so that your planning algorithm can query the states. And how do you do that in general? Besides saying that all the states would be translated into, a bit sequence, which is the same thing basically as an integer, right? From math point of view, there is no difference between a bit sequence and an integer. But here, just demanding that the simulator should give a complete description of like what are all possible states, that are just like not going to happen for most. I mean, in some cases, it's true. You can make it happen, but very often this is hard to do. All right. But this is global access. It would be nice if you could have it. Like this is the dream. So what else can we do? So the other one is local access. So in local access, you can only query the simulator at states which have been seen previously. So this means that you can basically checkpoint the simulator. So your planning algorithm is interacting with the simulator. The simulator, sorry, it's interacting with the big word. So first of all, there is the big word. State is coming in, this state. And then it's also interacting with the simulator, from which it learns about other states. Whatever states you have ever learned about, you can tell the simulator, go back there and simulate me a next state. So this is local access. It's local because only states that have been previously seen can be used. And clearly, this is more restrictive from the point of view of a planning algorithm, but it's liberating from the point of view of whoever writes the simulator. Because it's much easier to write a simulator that gives you local access. Yeah, actually, this is almost no restriction. Almost all simulators could be checkpointed. Some code could be added to them so that you say that, well, remember this was a state, and then you should be able to go back to this. So save the internal data that represents the current state of affairs in this world. So that almost always can be done. So this local access is fine. There is also, like, when you have the features, the feature would come in, and then you can query features for states that you have previously seen, but not for others. So this is local access. And there is a third thing, it's called online access. That's the easiest to implement. So in online access, you can't do this. You can't go back to previously seen states and then tell the simulator, simulate from here. You can only run full trajectories up to the end. Like, you just say, simulator, give me next state, give me next state, give me next state. But you can't manipulate from which state the simulator should simulate the transition from. Okay, so that's online access. So online access is even easier to implement, but it's even harder on the planning algorithms. And it is possible that planning algorithms that can have online access only are so severely restricted compared to planning algorithms that have global access or even just local access that they cannot do as much. They are severely, maybe they have to do a lot more computation just because of this. We'll talk about this later. So you may be able to prove things like that online access is really restrictive from the perspective of the planner. It's so restrictive that it's not just like or inability to come up with the right planning algorithm to use under online planning, but it's just like the problem is made harder, like just hard. Like the planner has to work more. So there are possibly real differences between how you can access the simulator. So here we have the global and local and online access. All right. So now the algorithm that we are starting from is just good old value iteration. So we want to do the local planning. And we start with value iteration because we know value iteration. It's able to calculate good policies for you. And the realization is that you can write value iteration in terms of this, I don't know, BAM on optimality operator acting on action value functions. So just go to BAM on optimality operator. BAM on optimality operator. And you just apply it to the identically zero function, let's say k plus 1 times. You get some action value function. And if you want to know how to act in a state S, you just query this at this state. And the realization is that this is just like, if you look at the definition, you need to iterate tilde k times. And that's just a recursive call, because then you have to plug in, like t tilde here. So t tilde applied to the previous queue. That's when you iterate things once. And so what that means, like, it means that, well, you have all of this plus all of this and then q, right? And then no, we could just do it one more. R plus gamma PM and so forth, right? Like, it's a recursive call, and then you can read it from backwards. Where, like, value iteration was just like this view that you're calculating these functions one by one, and then you calculated the function and you calculate the new function based on the previously calculated function. So that's like one view of value iteration. The other view of value iteration is just that it's like a big recursive call. Because now I can plug this in here, and this is just tilde k plus 1 applied to 0 and evaluated at SA. And then I can just do that with a big recursive call. So this recursive call, I call it Q because it calculates these Q functions or action value functions. They're pretty simple, right? Like if k is 0, so this calculates this. If k is 0, applying the operator 0 times, not applying it, so that just returns 0 because we're applying everything to 0, the 0 function. So then just return 0, okay? It's actually returning a vector of zeros. It should be, but it's like, okay, it's simplified pseudo code, all right? Because here you see, oops, this is a vector, right? Like, or this is an array. And if you're not in a base case, then there is at least one recursive call, and it's here, right? So here we are calling the same function, decreasing the counter from k to k minus 1, and then implementing just this lookup, right? So maximization first, and then summing over next states weighted by the transition probability. So that's your sum, then the gamma, then the reward, and then just return this for every. So if you want to have this at a state S, okay, so then this should be, we just want the A values of qk. So this function calculates really this. So it's A values. Then this should be like copied A times. So this here is A times. So these arrays have A elements. So at this state, we just do this calculation, and then we're done. And here is the recursive call. And okay, that's it. So very, very sweet, very short. The problem is that the cost of this is still, it's localized to us, but the cost of this is still too high. It has the number of states in it. And then the simple observation that we were making, that was made in the lecture, is that this cost, this dependence on the number of states disappears right at the moment when your system is deterministic, when it has deterministic transitions. So if the next state, given a state and an action, is given by this function g of SA. So that's what the simulator could give to you. And it is a deterministic simulator. It just gives you this. Then instead of this sum and the probability is only one at this single state. So we can neglect all the other states. There is no need for summing over states, right? So in the previous code, we had this sum over the possible next states. But now we don't need the sum of possible next states. We just ask the simulator, what is the next state? The simulator gives us the next state. We just plug that in. We know that the probability is 1 there, and it's 0 otherwise. So the previous code simplifies to this code. And in this code, there is no summing over states. So the complexity goes down. S is gone from the complexity. The complexity is only A to the power of k, right? And you can also imagine how this works. It is just like this recursive call, right? So how does this work? Like you have this state, and you have all these different actions for which you have to do the calculation. So this is this for loop. So the for loop starts to run. It takes the first action, and then it calls itself. And that's like expanding, like in a tree. And then, okay, so we are in this call, and now we are at this new state, GSA, right? So this is going, sorry, this is S, and this is GSA. And sorry, this is GS1 because that's the first action. And then this function is being called again, but with this state. But then the story repeats, like there is this for loop. So we're going to have all these actions. So it's like this fanning, this opening. And we take the first action, a equals 1, and we look at what is the next state there at GS1 if we apply the first action. So that's this. And so on so forth. This iterates k times until k is decreased to 0, in which case we're in the base case, we're just returning, 0. So when this happens, we return from this call the, sorry, I have to learn how to use this. Then the corresponding reward is added to this 0, and this is, some people call it backed up into this value. And this goes back up to this point. But okay, so first it goes back here. And then the next for loop, so there is a for loop here as well. There's a one but last state of the call. So then the next comes here, comes there, comes there, comes there. All of these are calculated. And once, wait, well, okay, so first, all of these are calculated. Then you take the max of those. Okay, for zeros, it happens to be 0. And then there is a first backup, which happens with a reward added to that value. So there is a reward added to that. And then this repeats. So that's the next for loop. So it's a depth first way of traversing this big tree. And the difference between the other view is that was like, it's like calculating first everything here, and then in the next layer, in the next layer, and the next layer, and so forth. So that was the value iteration view. And this is just like the depth first view. Okay. Okay. And of course, the cost of this, like we see that there is this big tree. It's a k-array tree. Sorry, it's an a-array tree of depth k. So of course, the number of leaf nodes is a to the power of k, and that's roughly the total cost of it. And this tree view kind of also suggests that there will be no way of doing better than this algorithm in general. I'm waiting for the for Google Meet to catch up because I flipped to the next page. I guess if there is a lot of drawing on a page, then it takes a while for them to flip. Come on. Oh, okay. All right. So there is this theorem that says that for whatever local planner you use, if it's a good planner, then it's going to cost you a lot. It's going to cost you as much as this value iteration algorithm is going to cost you. So you can't do much better than this. So notice that this is possible because the number of states is unlimited. So this tree example is always a possible example. And in particular, you can have this tree where you have this exponentially many leaf nodes. And just one of the leaf nodes is rewarding. And there's a self loop there. And if an algorithm wouldn't look at all the leaf nodes, then it could miss this rewarding leaf node. And it would suffer. And all the other rewards are 0. So it has to find this needle in a haystack. So that means that it has to look everywhere. So that goes back to this homework problem that you looked at before on homework 0, question 5. It was saying that if you have an array and you have a unique non-zero element in it, then no algorithm can do better than the algorithm that takes a random order and sequentially checks all the elements. So it's the cost of this unexpectation is going to be roughly the number of elements in the array divided by 2. And so this you apply to this situation, and you get this theorem. All right, so that's the whole thing for today. So questions from Slack. Farzaneh?
I wanted to, just before maybe we go to the questions,
Okay.
I wanted to say something. So like in the first algorithm we had, which was like 3 pages, like with the loop over the states.
Mm-hmm.
Yeah, so I remember just originally being confused of like the order that things were introduced. But so here it's not quite the local planning setting yet, in the sense that we're not utilizing any form of simulator, right? But what it does show is that like if we limit ourselves to not having a table anymore over the states and actions, in the sense of like for our value function, then we're limited to having to do this like sort of recursive algorithm for value iteration. But if we allow ourselves to kind of have a table for like the states and actions, then we can do like this like bottom up approach that you kind of drew on the next slide, right? And then we no longer have this sort of like exponential runtime in terms of the states and actions.
Okay, so you're flipping things on top of it. This is not really showing the other approach, which like the other approach is just calculate QK sequentially, starting with Q0, and then Q1 is just like T tilde applied to Q0 and so forth.
Exactly.
Then you get QK, which is T tilde applied to QK.
Yeah.
We don't have exponential cost, but the cost depends on the number of states. That's right.
Right, exactly.
So that's like memorization using values, and so that's what saved us from a trivial exponential cost.
Right.
Back in the day, when we allowed ourselves the luxury of touching every state, and this is just an intermediate step here, which is not good for anything. Just like a realization that this value iteration algorithm is really can be written in a recursive fashion, but it wouldn't be very good if you did this without memorization. If you do it with memorization, then of course, like it's gonna do its thing properly, and the cost of the recursive implementation is not going to be higher than the cost that you would have otherwise, right? Because it's just going to do the backwards calculation in a nice way.
Yeah, I get like it's really the memoization that allows you to like avoid this exponential term, right?
Yeah, I think that this is a very good talk point that if
and the reason I mentioned that is because I remember originally wondering like why this happened for value iteration, why we didn't just do it the way we did it in the previous lectures, because here we still allow ourselves to have technically like this table of transition probabilities P, which will be dependent on like the states, right? And so it seemed weird to me, but it makes sense in terms of like the natural transition to the deterministic case in the next slide, like you introduce.
And also later on, we like jumping ahead a little bit. No big secrets revealed. We're just going to subsample this. This is just calculating an average with respect to the next state distribution. So you could just like sample that with from the simulator M next states, and then take the average, and then you have the same algorithm basically, except that it's now using a simulator. So it's a very natural point to pivot from. So just the realization that all of these algorithms are instances of value iteration in disguise in some form or another. So value iteration is very versatile. It's like, well, it's like calculating optimal values, and you need the optimal values or some estimates of them to come up with how to act. And how would you do that? Well, it's only value iteration. There is nothing beyond value iteration. All these algorithms are implementing value iteration, but maybe the ordering in which they are doing the updates is different. And then sometimes they take some shortcuts. That's why. I prefer the presentation this way. I think it's just connecting that these tree-based calculations are really just implementing value iteration in recursive fashion. I think that that's really important. Because otherwise it might seem that, okay, this is a little bit different, but no, it's really the same.
Yeah, yeah.
And if you want to analyze the tree-based calculation, the best way is just to think about it as if it was implementing value iteration. Really. Oh, and so this memoization. So I don't know, like I didn't grow up with CS, so I heard about memoization, but like it's this thing, if you haven't heard about, that if you have this function Q, then it could be a little local memory, and it checks whether the arguments are in this local memory. So you would add a little associative array that maps inputs k as pairs to values, and it builds up this memory. So the first thing the function would do is to check whether k and s is already in the local memory, but if we already calculated this thing. If we already calculated this thing, we just return the memoized, the remembered value, and otherwise we go into the call. So this is the memoized version of it. And the memoized version will not do more work than standard value iteration would do. It shortcuts the recursive calls, because it doesn't go into the recursion when it notices that for some state, we already calculated the value. So if you have a small state space, and because of that, value iteration would save some work. So value iteration is not going to do more work than, I don't know, s to the some power 4 times a over 1 minus gamma. It's never going to do more work. That might be less than s times a to the power of k. If it's less, then this memoized version of the algorithm is not going to do more work. It's going to do the same amount of work because it remembers all these values. And then it's not doing the recursive call. So sometimes, if you like, that's not our typical way of thinking about MDPs, but you can think about MDPs that I don't have many states, and not having many states is going to save you work. That's a really lucky case. And that's kind of the story with dynamic programming and memorization in general. That's how you save space. That the number of states itself is not too large. But now we are in this other realm where we start to ask questions about what if that is not the case. Well, then you have to invent other things. And now we are going back a little bit. It's almost like forgetting about this great device of memoization, just like looking at the tree, and but then realizing that, okay, but this at least the compute time is independent of how many states you would have. Because if you just insist on this way of implementing value iteration, then if you have a large number of states, then that's gonna kill you. And this may be better. And of course, if you add memoization on the top of any of these routines, then that can only be as the best of the two, right? Like the best of both worlds. Okay. All right. So time for a question. For something.
Yeah. Should we wait for a slide to flip, or?
Yeah. Well.
Okay. There we go. Okay. My question is again about MDP simulator and assumptions on that. So from what I understood from the definition, our assumption is that we are working with a forward model because given a transition of SA, reward, and S prime, next state, we are inputting current state and action to the simulator, and then we get reward and next state. But what about backward model? Like in backwards, we are having our current state as like S prime, and we are trying to get to the previous state, right? And so like we are inputting S prime and action, and we are expecting to get the reward and state S, which is the previous state, and it already happened, right? So for forward model, it's pretty straightforward because like if we are looking for like a distribution model, we are saying that like the probability of S prime and reward given state S and action A would tell us that what would be the next state and reward, right? But for backward models, we might have more than one state taking the same action and going to next state S prime, right? Like S1 and S2. And we really don't know like what would be the distribution over them. And it would be based on like what policy we took before getting to like state S prime. So in that sense, I was wondering how this P of A S would change for backward models.
Yeah, these backwards models are kind of weird to me. I think that I view them as an attempt to make certain algorithms work when you can even meaningfully define. So what you're asking is really whether these backwards models can be meaningfully defined at all. It's like what does it mean that you want to know what state you could have come from given an action? Like, let's say you fix an action, right? And you arrive at some state S prime, and then you want to know like where could I have come from? So maybe this is not uniquely defined. Even for deterministic dynamics, it can very easily happen that, for example, you can have a little robot, again, in an enclosure, and maybe it's a wheeled robot in this case. It's a little cart. It can go left and right. And if it bumps into this wall, this is a wall, it just stops. But maybe the last step that it took, it was going, I don't know, like the action was to go left, but we were too close. We are measuring, I don't know, 0.1 seconds later, and we bumped into the wall, and we just stopped there. But we could have been here, or we could have been, I don't know, like in any of these places, right? Like if we're close enough to the wall, then a wall is going to stop us in the next 0.1 second. And there is no unique way of telling which position we came from. So the systems can just like forget the past. Like the new state is not a new state, and knowing that you were going left doesn't tell you where you were coming from at all. So sometimes it's not possible to invert these things at all. Like it's not mathematically well defined. And then people are trying to do certain things, but it becomes hard. The way I see these things is that, well, if you have a robot arm that is working in an environment where it cannot bump into anything, and then somehow like this invertibility does hold, then that might allow you to design algorithms that take advantage of this. And then people were doing this in robotics for a while. But I think it's better to avoid this if one can, because these backwards models are it's gonna be limiting, right? Like it's a lot of times they're not well defined, and yeah, it makes me worried if we are losing the baby with the bathwater if we start working with backwards models, so or inverse models. So I wouldn't do it. Yeah, I don't know. I'm not really answering the question because I mean, how does it affect the theoretical guarantees in local planning in every possible way? Like this is just a different set of assumptions. So if there is a well-defined inverse dynamics or backwards models, then sometimes you can have stronger guarantees or algorithms that are more efficient. So in the area context, I know at least one paper that's talking about this, but this is more like a patch. Like they were trying to come up with some algorithm that would have worked in general, but then they noticed that they can only do this if this extra condition is met that the dynamics can be inverted, and then so they add the condition that the dynamics can be inverted, but I can't invert dynamics in general. So it has similar problems as with the global access that, well, it's wishful thinking. I wish it was true, but it's not quite true. So to me, the forward dynamics is natural. That's something we can easily implement and routinely implement simulators with the forward dynamics, not with backwards dynamics. Show me one simulator where backwards dynamics is implemented.
So actually, I've been working on a research project. That's why I originally asked this question.
Okay, you have.
Yeah, we have some results in different benchmarks, and also intentionally designed environment to show that backward models are performing better and are more reliable than forward models in terms of imperfect MDP simulators. And my only issue for now is that how can we approach this problem of providing some theoretical guarantees that we really can if there is a well formed MDP simulator, we can have some theoretical guarantees on some good planning. Experimentally, we showed that they are really performing better, but for theoretical part, I'm not quite sure how to approach. I was thinking maybe we can get benefit from different policy pi that we have probably taken before getting to this state as prime. But I'm not really sure how it will,
It reminds me, this whole thing reminds me of that in classical planning in AI, people talk about this reversible actions or something like that, which is basically that you can go backwards. And then there is goal-oriented planning, right? So in order to meet this goal, I need to do this. In order to meet that goal, I have new goal now, because I need to achieve this state in order to meet this goal. And for that, I have to do this. I have to do that. And then there is something then you have a bi-directional planning algorithm, right? And actually, in AI, people have been looking at this advantages of bi-directional planning and so on and so forth. In general, you could say that at least you expect, if like previously we had this tree with a depth of k, and you had a to the k leaf nodes. If you can do the backwards thing as well, and you have like the top-down version of this, and then you can cut this in half, and this is k over 2, and this is k over 2. And so this becomes not a to the power of k, but it becomes a to the power of k over 2. So it's like basically square root a to the power of k. So as if like you were able to plan with square root number of the actions. So if you can do the bidirectional planning, then that's usually the benefit of it. That the branching factor can be taken to the square root of the branching factor that you had before. And so there were some papers written about this. I don't know whether it's there is a fully fledged theory, but like this is the intuitive picture. So you can expect a reduction of cost of this order of magnitude, which can be big, right? Like it's in an exponent, it's a factor of 2. If you would normally just say it's a factor of 2, it's not really big, but it's in an exponent, right? So if you really have to have like 10 steps to reach the goal, then there are only 5 steps here, 5 steps there. It's like you had, I don't know, 10 actions. 10 to the 5 is fine. 10 to the 10 is not fine, right? It's a big difference. So maybe look at, I don't know, this classical planning in our department. There are all these planning people, and I've been looking at this. And Rob Halty, I think, had some paper with bidirectional planning and then some observations there. Or bidirectional search, they call it. Yeah, in the context of, I don't know, Ara, I'm a little skeptical, but okay, whatever it takes. I mean, maybe it's okay. It just depends on. I mean, the problem itself is interesting. It only depends on how widely this can be applied, and there I have some doubts. But even if there is some niche applications where this represents a huge savings, I think that that's great. Like we should take it. Any savings is good. All right, good. Someone wanted to say something. Alex, maybe?
Oh.
No?
I
was just going to ask about, so the inverse model just being the inverse of the transition dynamics.
Yeah, it's like if you have a function, like you can think about this as like, okay, for every action A, there is a function that gives you next states. So now you can try to invert this function. If the function has an inverse, then okay, you have the inverse dynamics.
So would the inverse be like a conjugate prior in this interpretation, or?
Oh, if you have probabilities, then I have not the faintest clue.
Oh, okay.
Stochastic systems, it's well defined. If it's stochastic transitions, then I don't know. Like you can try to think about some way that you can invert these transitions, but I don't know what the right interpretation and whether that interpretation is going to buy you something like what I was talking about, like cutting something in exponent because you can do bidirectional.
Okay, yeah, because I was going to say, if you invert that, the eigenvectors may be greater than 1, and then if you take some like infinite like you just keep applying the operator infinitely many times, it may diverge, not to like a steady state.
I mean, the paper that I remember that was this backwards model, but I think that was slightly different.
Okay.
It was a paper by Yasin and Peter Bartlett, and I don't know who else. It's about linear programming applied to RL and in some planning context. It was more like that So we have P, A, S, and S prime.
Are we in tabular stochastic setting or tabular deterministic?
Stochastic. They were in the stochastic setting. If we are in the deterministic setting, then this view in the top is the right view. So or that's kind of the standard view. So they were talking about that. Normally we think that you can input A and S, and you get all the values with S prime. And they were thinking about that this array can be indexed maybe the other way around. I don't know what it was like. I forgot. It was not supernatural. So maybe it was that, yeah, it's like the elementary operation that you can do is to get this vector. For a given S prime and an action A, you get a vector over states, which represent all these source probabilities. And then somehow, maybe I think that they made the assumption that there are only finitely many and a few number of possible states where this probability is positive or something like that. And they can do something with that. So that's how they are using this inversion of like, where did I come from? Like, where are these probabilities positive? Maybe they're not positive at too many places. They're only positive at 10 or like a constant number of places. And somehow someone's able to tell you which are these states. It's like here in this little figure, we are in this terminal state, and then the action is left. Then someone would give you that, oh, all these states are possible, and these are not possible. So they like you would have this compressed or sparse representation for the possible sources. I think that that's what they were doing.
Okay.
So Chava, I have like another question regarding this. Like it's kind of idea. I don't know how much it's valid or not. So if we assume that the policy is fixed, then this means that we could have the probability distribution over previous states, right? So we won't get to this problem because we already have that distribution over previous the probability distribution over previous states because the policy was fixed. So can we assume that we have, I don't know, n number of problems with different number of policies, and then we try to come up with like a kind of objective function that we can optimize and then choose some kind of mixed policy among those policy fixed problems, and then generate the MDP simulator for backward models.
Yeah, I don't know, maybe, but it's getting pretty wide for me. Yeah. Okay. All right. I was planning some discussion because I said that we're gonna be done, but we were not. So we're gonna save the discussion for some future time. The discussion was supposed about computational complexity and computation models. It's like a general philosophical topic, but I'm just gonna save it for next time. All right. Good. This is for the week then. See you next week. Have a good weekend. And thank you.
Thanks.
Thank you.
See you.